Welcome to 10.4, polar coordinates and polar graphs. So we are going to look at some coordinate conversion. We're going to be graphing some polar graphs, and we're going to talk about slopes in polar form and tangent lines. So the first thing, let's go ahead and look at coordinate conversion. If we have the polar coordinates r, theta, and they're related to the rectangular coordinates x, y, by the following. So we're going to let x equal r cosine theta, y equals r sine theta. So then our coordinate points, this is our x, y right here, okay? And then tangent of theta equals y over x, and r squared equals x squared plus y squared. So if we take a look here at this graph, if we have a circle with a radius r with this angle theta, this would be our x direction, this would be our y direction, so then we can go ahead and say that the Pythagorean theorem, x squared plus y squared equals r squared, and then tangent of that theta does equal y over x. So we're going to get right into our first example of some conversions, converting to rectangular, so in terms of x and y, and then converting to polar in terms of theta and r. So the first one, so we want to convert to rectangular. So we have r is equal to 5 cosine theta, all right? So we need x and y, all right? So if we multiply both sides by r, that's going to get us to r squared. We know what r squared is. R squared is x squared plus y squared. By multiplying the right side by y as well, we get this r times the cosine of theta, which we know is x. So now we have our equation in terms of x and y. Now we'll just kind of clean it up. So we subtract the 5x, and I leave a blank because we're going to have to complete the square here. And then plus y squared, and leave a blank over here. So we needed to complete this square just to kind of get it into a nicer equation for us. So we're going to take this middle term, divide by 2, and square it. So 5 divided by 2, square it, we get 25/4. Whatever we do to the left, we have to do to the right. And so we clean this up, and we end up with a circle with center of 5/2, 0, and a radius of 5/2 as well. Okay, so there is our equation, converting it from polar to rectangular. Now we're going to go in the other order. So we are going to convert this polar coordinate, or sorry, this rectangular coordinate to a polar coordinate, okay? So again, we know x squared plus y squared equals r squared. We need to know what r is equal to, okay? So plugging in this for x and 8 for y, we end up with r equaling 4√5. Tangent of theta equals y over x. So again, just plugging in 8 for y, 4 for x, we get tangent of theta to be 2. So then theta is equal to the inverse tangent of 2. So if we want to rewrite this in our polar coordinates, r, theta, we have our coordinates right here. All right. Now we're going to get into some graphing examples. Okay. And we'll look at kind of 3 scenarios. One graph where we get r equals 2. This ends up being a circle with a radius of 2. Okay, so this consists of all points, or of all points that are 2 units from our pole. We call the pole 0, 0 using our unit circle. Okay, so graphing in that polar aspect. Graphing theta equals pi over 3 is simply all of the points that consist or make an angle with theta being pi over 3. So this is actually called a radial line, and we're looking at the theta being from the positive x-axis. So everything here along this line creates that angle there. So that's a radial line when we're graphing theta equals some value there. This last one isn't as obvious. Okay, so if we wanted to graph r equals the secant of theta, how do we get this to be a vertical line? Okay, so it ends up being a vertical line, but how? So let's look into it, all right? Because again, it's not obvious. So what we need to do is we actually need to convert, all right? So what we can say is, all right, if r equals secant of theta, that's really like saying 1 over cosine of theta. If we multiply both sides by cosine of theta, we get r times the cosine of theta equals 1. Well, we know r times the cosine of theta is just x. So we end up with x equaling 1. So we do end up with a vertical line when we're graphing r equals secant of theta. Or anything of the like, you probably have to convert to see what we're dealing with. All right, let's move on to the next page and get into actually graphing these polar functions. Okay, now we're going to get into actually graphing or plotting these polar graphs. All right, so if r equals 3 sine of 2 theta, the first thing I always do is I kind of rewrite this as y equals 3 times the sine of 2x, because we're good at graphing the sine function. All right, 3 is our amplitude, so when I set up our graph here, I know we're going to go from, oh, that should say -3. All right, that should say -3, but we should go from -3 to +3, okay? Then I'm going to take this 2x, right, this period, and we're going to place it between 0 and 2 pi because I have to figure out, all right, what is each period going to be, all right? Now, we're going to graph the entire thing. We're always going to graph from 0 to 2 pi. But if I divide everything by 2, I know each period is going to go from 0 to pi. All right? So as we're marking everything off, I always start 0 to 2 pi. I know when we get to pi, that's going to be our 1 period. All right? And we'll be able to continue the trend. So we've got pi over 4, pi over 2, 3 pi over 4, etc. And now we're going to go ahead and graph the sine function. Okay, so hopefully this aspect isn't anything new, but here we go. So we're plotting it. We know we start at 0, 0. All right, we get back down to pi over 2, and we're back to 0, and then we go negative, and we're back to pi, and so on and so forth. Now you notice I've got different colors here. So what we're going to do is we're going to break up the graph at all of these points here that are highlighted. Okay, when we get to that +3 or -3 aspect, okay? So what we should notice is that at pi over 4, we're positive, right? We're at +3. So r is positive. So when we graph from 0 to pi over 2, we're going to be in that quadrant 1, okay? So what's that going to look like? Well, let's go ahead and graph that portion of it. So I'm going to move over to the graph. I've kind of already got it situated here where we have, I broke it up by pi over 4, pi over 2, etc., 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 because these are going to be our big pieces here. All right. Now, our radius is still 3. Okay, so r equals 3. Our radius is still 3. So as we begin to graph this, let me, here we go. I'm going to start at 0, and we go out in quadrant 1, and we come back around. So there is our first leaf. That's the green portion of our other graph. Okay, now let's go back to over here. So as we graph this next portion, what we should notice is that 3 pi over 4, our radius is -3. Okay, it's -3. So even though we're at 3 pi over 4, our radius is negative, so we have to go in the other direction. So what does that mean? It means even though I'm here, it's a negative radius. So it's almost like looking in a mirror. So we're actually going to draw our graph over here. So the blue portion of our graph, after I stem here, we're going to come back and we're going to wrap around, okay? Because our radius is negative. At 3 pi over 4, we go in the opposite direction, right? Now let's go back to our graph. Now we're in the pink section. So we're here, and what we should notice is at 5 pi over 4, our radius is positive. It's at +3, so we can stay in that quadrant 3. All right, so as we do that, I'm going to change my color really quickly, and we're going to zoom over to our graph. So now we are at 5 pi over 3, or sorry, 5 pi over 4, so that's here. So after I made that blue strip, we're going to continue on. Our radius is 3, and we circle back to 0 as we get to 3 pi over 2. Okay, so far we're here, and the direction that we went, We started at 0, 0. We went out, radius of 3. We had a positive radius. Now at 3 pi over 4, we had a negative radius, so we're actually going this direction. And then we wrap back around. And now at 5 pi over 4, we have a positive radius, so we can stick right to it, wrap back around. So now looking at the last portion here, now we're at 7 pi over 4, but because our radius is negative 3, we have to go in the opposite direction of 7 pi over 4, okay? So what's that going to look like? And that is going to look like the following, okay? So now after we get back to 0, 0 from our pink section, we continue curling around and we go in this direction. Because our radius was negative at 7 pi over 4, we go in the opposite direction. It's almost like looking in a mirror, and now we're back to 2 pi. We've finished our rounds, okay? So again, it's all about positive versus negative at that leading point, that highest point. If your radius is positive, you go out in that particular direction. If your radius is negative, you go in the opposite direction. It's like looking in a mirror. So then we have our final graph, this beautiful looking flower. And you can kind of follow my motion here of what it looked like if we were doing one smooth curve all the way around. Okay? All right, so now we're going to get into slope in polar form. Okay, so this is kind of like the slope in the parametric form that we learned the other day. It's just in terms of theta, okay? So if f is a differentiable function of theta, then the slope of the tangent line to the graph of that r equals f of theta at point r comma theta is the following. So dy dx, still the same, is going to be the derivative of y in terms of theta over the derivative of x in terms of theta. Now remember, if y is r times the sine of theta and r is equal to f of theta, like we said up here, okay, then all we're doing to find the derivative is simply the product rule of this function right here, okay? And the same thing, we know x is equal to r times the cosine of theta, so r is really f of theta, it's that function in terms of theta times the cosine of theta. So to find the derivative again, we're just using the product rule for dx d theta, and that's here. So we'll get some practice there, all right? Then one other thing to talk about is horizontal tangents. Horizontal tangents occur when dy d theta equals 0, and vertical tangents occur when dx d theta equals 0. If both the horizontal and the tangent, or the horizontal and the vertical tangent equals 0 at the same value, no conclusion can be made about those tangent lines, and we'll see an example of that later on. The last thing before we get into our final example is talking about these tangents at the pole. So the pole is the point 0, 0, right, or 0 theta, or alpha, I should say. So if f of alpha equals 0, and f prime of that alpha, that angle, does not equal 0, then the line theta equals alpha is a tangent line at the pole to the graph of r equals f of theta. So if we have our pole, this is the tangent line, or the point 0 alpha, all right? The slope is going to be tangent of that alpha, that angle. Okay, so if we have something like this, and this is our tangent line through the pole, okay, or at the pole, and our theta, or our alpha, is pi over 6, then the slope is going to be the tangent of that pi over 6, okay? All right, so now we're going to get into our very last example, but it's kind of a hefty one. So the first thing we're going to do, given our polar function, is we're going to find the slope of the tangent at theta equals pi over 6. All right, we're going to find the points where the tangent line is horizontal and the points where the tangent line is vertical, okay? So the first thing we want to do is we want it in terms of x and y, right? So again, we know x is equal to r times the cosine of theta. We know r is equal to 2 plus 2 cosine of theta. So we just make that substitution and we get what x is really equal to. Same thing for y. We know y is equal to r times the sine of theta, so we're just substituting what r is, and we're cleaning it up. So we have our y value, okay, or our y function. And now the first thing we're going to do is we're going to find the slope of the tangent at theta equals pi over 6. So remember, the slope is dy dx. Okay, so what is dy dx? dy dx is the derivative of y in terms of theta over the derivative of x in terms of theta. All right, so I just took what our y function was, and I found the derivative of it. Okay, so 2 times the cosine of theta, and then we have to use our product rule for this portion, and that's where we get 2 cosine squared minus 2 sine squared. Same thing for our x. So 2 times the cosine, taking the derivative of that, we get negative 2 sine, and then that power rule here, bring down that power. So 2 times 2 is where I got 4, and then cosine times sine, all right, and it should be negative 4 because taking the derivative of cosine is where we get that negative sine from. And now I'm just going to evaluate this at pi over 6. Okay, so we're going to plug pi over 6 for all of the thetas. And when we do and we clean everything up nicely, we end up getting our slope to be negative 1. Okay, so our slope is negative 1, but let's go ahead and take it one step further. What is the point of tangency? Okay, so the point of tangency, now we just need to get our r value. Okay, so we know the slope is negative 1, but where does this occur? Well, we know it occurs at pi over 6 for theta, so we're just going to plug this into our r function at the very beginning, and we get r to be 2 plus root 3. So the point of tangency is 2 plus root 3 comma pi over 6. So that's our r comma theta. All right? And now the next thing we're going to do is we're going to talk about the horizontal tangent. Okay? So remember, the horizontal tangent is when dy d theta equals 0. So we already found what dy d theta was. It's this guy over here. So we're just going to set that equal to 0. So I'm going to zoom in now. Okay? Setting that equal to 0, I can divide everything by 2. All right? And then making a trig identity substitution, we know sine squared is equal to 1 minus cosine squared. This just helps me have a function completely in terms of cosine. Cleaning things up and putting it in proper order, I can now factor this function. Right? This is almost like 2x squared plus x minus 1, where x is just cosine. All right, so this factors as 2 cosine theta minus 1 and cosine theta plus 1. Setting each of these equal to 0, for this guy, we get cosine of theta equals 1/2. So that means theta has to be pi over 3 or 5 pi over 3. For this factor here, cosine of theta equals negative 1. Well, when does cosine of theta equal negative 1? When theta equals pi. Now I'm going to hold off talking about the points, the horizontal tangent points, in just a second. Let's go ahead and find the vertical tangent points, or at least the theta values. So again, vertical tangent is when dx d theta equals 0. Now we already found dx d theta in example, or in part A, so we're just going to set that equal to 0. Dividing everything by negative 2, we get this guy right here. We can factor out a sine, and we're left with 1 plus 2 cosine of theta. Setting each of these factors equal to 0, sine of theta equals 0 when theta is 0 or pi. Cosine of theta equals negative 1/2 when theta equals 2 pi over 3 or 4 pi over 3. Now what we should notice, and this was the scenario we kind of talked about earlier, is our pi over 2, pi is when both dy d theta and dx d theta equal 0. We can't have this. This doesn't help us out, all right? So this is when they both equal 0. All right, so they both equal 0 at theta equals pi. So this is a special case, okay? So this is a special case, and this is something we'll talk about later. So what that means is we just have to take those values off the docket for now. Those don't count as possible points of tangency for horizontal or vertical tangents, all right? So now let's go ahead and just finish the problem up. So let's find those horizontal tangent points and those vertical tangent points. So the horizontal tangent points then are when theta equals pi over 3. And when theta equals pi over 3, we're going to plug this back into the r function up above. We end up getting r to be 3. When theta is 5 pi over 3, we end up getting r to be 3 as well. So we have the 2 points of horizontal tangents, okay? They occur at these 2 points. The vertical tangent points, we end up with theta equals 0. When we plug in, we get r to be 4. When theta is 2 pi over 3, we get r to be 1. And when theta is 4 pi over 3, we get r to be 1 again. So we end up with 3 vertical tangents and 2 horizontal tangents. This other case, when theta equals pi, that is a special case we'll talk about later on. So you can kind of see here as we look at this graph, yeah, it looks like we've got 3 vertical tangents and 2 horizontal tangents, one at the top there, one at the bottom. All right, if you have any questions, let me know.